Hello everyone. Today we will talk about the specifications of compositions, atomic percent, mass per volume concentrations. For diffusion, we use the average atomic weight and average density for materials such as alloys that we mix several materials with each other. And after that, we will go through the key formulas for each concepts and then solve a case study that cover all these aspects. So you can see how they are applied in practice. By the end of this video, you will understand to how convert between weight percent, atomic percent, calculate mass per volume concentration that you use for diffusion calculations, and determine the average atomic weight of an alloys and computing average density of the alloy using the rule of mixtures. And then we have solve one case study or example step by step, applying the equations we discussed today, and we can see how to complete work flow from compositions to diffusion relevant concentrations. Okay. First, talking about weight percent. Weight percent is one of the most common ways to express the compositions of the materials. It tells us the mass fractions of each element or component in the alloy relative to the total mass that we have. For example, if we have only two elements, 1 and 2, so C1 is mass of element 1 per total, that is M1 plus M2 times 100, or C2 is M2, M1 plus M2 times 100, and the summations of them should be 100. But if we have more than one element, we use this. For example, C1, if we have n element, should be M1, M1 plus M2 up to Mn, but times 100%. Okay? And the summations of all CI should be 100. What is the applications or functions of the weight percent? Specify compositions by mass for weighing alloy fabrication, recipe control, and data sheet that we have. If you see additive manufacturing in all of that, we have the weight percent, for example, how much percent of A, how much percent of B or C, or all of that. Okay. Then we have atomic percent. Atomic percent express the fractions of atoms of a specific element relative to the total number of atoms that we have in alloy. It is useful for understanding the actual atomic distributions or contributions in a material. For example, if the mass of component 1 be M1 and atomic weight be A1, you know that mass if number of atoms, for example, times atomic weight. So here, number of mole, for example, in atomic weight, 1 give M1. So how much N1? It should be M1 per A1 and M2 per A2 is this. What about these fractions, the N1 per total number of atoms or moles that we have? Should be N1 per N1 plus N2. As it expressed at percentage, multiply 100 and write in M1 A1 and instead of N2 M2 A2. And again, for all fractions that we express as percent, the summations of them should be 100. So C prime 1 plus C prime 2 should be 100%. If only we have 2, means these equations that we wrote here, it only when we have 2 components. So if we want to express C prime 1 as a function of C1 and C2, C prime 1 should be C1A2, C1A2 plus C2A2, or C prime 2 is C2 times A1 per C1A2 plus C2A1. What is the applications of that? Used when atom counts matters for crystallography, phase diagram, or some things that instead of expressing as a weight percent, we express as atomic percent. Okay. Conversion between Ci and C prime I. Sometimes, for example, we have weight percent. By having weight percent, we want to find the atomic percent. So conversion relations allow us to switch between weight percent or Ci's to atomic percent or C prime I's. So these equations are essential for linking mass-based and atomic-based compositions in alloy. So you see here, in previous slide, we wrote C prime I's as a function of Ci's. Here you see the vice versa. C1 is C prime 1 A1 divides C prime 1 A1 plus C prime 2 A2, or C2, that is weight percent of the component 2, is C prime 2, that is atomic weight percent of component 2 times A2, and you know A2 is atomic weight of component 2, divides C prime 1 A1 and C prime 2 A2. Again, what is the function or applications of knowing these relations? Converts mass-based data from lab weighing to atomic compositions used in macrostructure analysis and vice versa. Okay. Average atomic weight. The average atomic weight of an alloy that show by AV is abbreviations of average, is calculated by weighting the atomic weights of each element by their atomic fractions. It gives a single representative atomic mass for entire alloy. So A average, what is Xi is the mole fractions. Mole fractions is C prime, but divide 100. Why? Because for C prime, if you remember, we multiply in 100. But if we only want mole fraction, should divide that, yeah? So A average is C prime A1 per 100, yeah? And you see here, it's this A average. It is as a function of C prime. It is as a function of C1. So A average is 100, C1, A1, C2, A2 if we have only two components, or we can write that as C prime 1, A1, C prime 2, A2 per 100. Here is the function of atomic percent. Here is the function of weight percent. Okay, so what is the function of that? Convert mass in grams to moles to atoms of the alloy used to get some atoms per mass to calculate molar quantities to relate unit cell mass to number of atoms. And here, average density or row average. Average density or row average can be estimated using the rule of mixtures. It combines the density of each component weighted by their volume or mass fractions to give an overall density for the alloy. What is row average? Row average should be total mass. So it should be total mass per total volume. Means M1 plus M2 per V1 plus V2. If you substitute in a set of V1 and V2, for example, rho 1 is M1 V1, so V1 is M1 divide rho 1. So it should be M1 plus M2, M1 per rho 1, and M2 per rho 2. If we write this, you see that we reach to this equation. Row average is 100, divide C1 per rho 1 plus C2 per rho 2. And you know that what is C1? It's the weight percent of component 1, and C2 is weight percent of component 2. And rho 1 and rho 2 are densities related component 1 and 2. If we want to write as atomic percent, we can again So a row average is C prime 1 A1 plus C prime 2 A2. Divide in denominator, we have C prime 1 A1 per row 1 plus C prime 2 A2 per row 2. What is the function or applications of knowing this? Needed to convert weight percent to mass per volume concentrations, to compute the unit cell mass, to estimate bulk properties that depends on the density. Always we need the average density for most of the calculation that we have. So we should calculate that as same as average atomic weight or A average that you saw in previous slide. Mass per volume concentrations that use for diffusion or C double prime I it's very important. Mass per volume concentration or C double prime I represent the mass of an element per unit volume of alloy. Yeah, you know that mass unit of the volume is rho. So volume or unit volume is 1 per row. Okay, 1 per row. And it's used for diffusion calculation that you see in next slide. So we use by mass fractions or omega I. Omega I, the difference between omega I and Ci. Ci means omega I multiply 100. So for having omega I, we divide Ci per 100. And we know the average density or row average in gram, for example, per centimeter cube. So C prime I as a gram per centimeter cube is WI times row average. If we substitute here, should be CI row average per 100. If we want C prime I as a kilogram per meter cube, it should multiply in 1000, yeah? We find row average in previous slide 100, C1 row 1, C2 row 2. If we substitute here, these 100, 100 cancel out each other. So C prime 1 is C1 per C1 per row 1, C2 row 2 times 1000. And again, we have for C prime 2. But if we want to express in gram per centimeter cube, only we use this. Means instead of multiply in 1000, means divide 100. If you remember, I told that we use C prime I for the calculating the diffusions. So fundamental role, the mass per volume concentration is the primary variable for measuring or quantifying how much of the this solute is present at any point in a medium, and enabling calculation of concentration gradient, which drive diffusion. In chapter 6 of the book that you will see that we use the Fick's law. And what is the Fick's law? Fick's law is J equals minus D, C per dx. What is this C per dx? Is the gradient. This C prime, or means the concentrations that we are using that, or mass per volume concentration, and D is the diffusion coefficient, and J is the amount per unit area per unit time, means how much of the material or diffuse or transparent per unit area or cross-section area. So what is the unit for J? For example, it should be kilogram meter squared per second or time. Okay, here you see the examples. We have one alloy that contains of 3 elements. The first one is nickel, 120 pound mass. The second one, 80 lbm or copper. And the third one, tin or SL, 5 lbm. At first, we have been asked to calculate the compositions of alloy in weight percent. The second one, atomic percent composition for each element. The third one, concentrations of each element. or kilogram per meter cube for alloy that I told that used for diffusion for calculating J. So we are looking to C prime. At D, calculate the density or average density of the alloy. No need to say that when we say the density of the alloy is the average or mix of that. So we should calculate average density. And D, determine the average atomic weight of this alloy. We need several data. For each of them, we need knowing the atomic weight. You can use the table that we have for nickel, copper, and S, and you see atomic weight in these tables. And in this column, we see the density per gram per centimeter cube. What should we do? First, convert the mass of all elements from the pound to gram. Consider 1 pound is 453.59 grams. Multiply and find the mass of each of them as a gram. What is the total mass? Total mass always, so M total, it depends how many component or element we have. Here we have 3, so should be M1 plus M2 plus M3. M1 is mass of nickel, M2 mass of copper, and 3 is mass of Sn or tin. So we find the total mass. Ci or the weight percent for the nickel is the mass of nickel per total mass times 100%. So here you see 58.52%, for example. For weight percent for copper, mass of copper divided per total mass. For this alloy is 39%, for example. For weight percent of Sn or tin, the mass of tin per total mass, that is here 2.44. Another way that you see that you were right in calculation means adding all of this C that you drive, and you see that you are reached to 100% or no. When you reach to 100% means you were correct. Atomic percent. Atomic percent means the fractions of the mole or atomic number times 100%. You remember we had the mass of each element was the number of atoms at that element times the atomic weight of that element or component. So vice versa, Ni is Mi divide Ai. We have the mass of each component, we calculated, and we know the atomic weight from the table that you saw at 2 slides before. So we find the total, the moles of each component. For total moles is N1 plus N2 plus N3. Substitute here, and it is the total mole. What is atomic percent? The mole of each component divide total mole times 100%, and we find. As same as another fractions that expressed in percentage, the summations of all of them should be 100. You can check that and see that you are correct or no. The next one, mass per volume concentration, or C double prime, that you use for what? Use for concentration or calculating the diffusion concentration. We need the weight or mass fraction. Mass fractions means here, for example, C1 divide 100, C2 divide 100, C3 divide 100, as you see here. For 1 per row average, okay, what is 1 per row average? Means 1 per M1, V1, okay. If we wrote that, it should be mass per row N1, mass per, for example, mass percent row C, this mass percent per row Sn. Okay, we do this and, sorry, and we find 1 per row average as this. Reciprocal of that, you find the row average as a kilogram per meter cube, or for example, gram per centimeter cube. For using that equation, or C double prime, if you remember from previous slide, was weight percent times row average, weight percent of each of them, times 1,000. If you want expressed as kilogram per meter cube. Okay, we found WN1, WCU, and WSN. For each of them substitute, row average we calculate here, times 1,000, and you see the concentration for each of them. And density for the alloy, previously we calculated that, no need any new calculation, only substitute from here, and it is for part D. And the last one is E, or atomic weight, or average atomic weight. If you remember, we had two formula, one of them as function of Ci and another function of C prime I. So for Ci is 100 divided per summation Ci per Ai. We know Ci for each of them, we know atomic weight for each of them, substitute here, and you find the average atomic weight for this alloy as 61.26 gram per mole. Okay, hope this video helped you to understand the topic better. As a special thank you, I have created the free study guide with everything that today we covered. To get your copy, just find the link in the descriptions of this video. Your video helps me improve these lessons. Leave a comment if you have any questions, and subscribe that you will not miss any video or upcoming videos in future. Thank you so much, and bye-bye.